We're going to take a look at questions 6, 7, and 8 on worksheet number 1. Number 6 says a 2.00 kilogram rock is dropped from rest. From rest means VI is equal to 0, right? From the top of a 30-meter high building. What's the ball's momentum at the time that it strikes the ground? This is similar to the example question number 2 that we did yesterday. We want to find the momentum after what? After it's accelerated, right? So what do we need? If we want to find the final momentum after something's happened, we need to find the final velocity, right? Yeah, exactly. Let's write down some givens, then let's find the final velocity, and then let's find the final momentum from that. All right, we have a mass of 2.00 kilograms here. What else we got here? What's this 30 meters thing here? What's that? Yep. Yeah, we'll call that the displacement. If we're going to call it the displacement, let's make it negative 30 meters because it ends up below where it started. Some people might like to call it the initial height. If you're going to solve that question for the final velocity using conservation of energy, mgh equals 1/2 mv squared, probably going to call it a height. If we're going to use one of the acceleration equations, then we're probably going to call it delta d, the displacement. Doesn't really matter though. Delta d is a vector. We need the negative associated with it though. All right, what are we looking for here? What else we got? There is something else if I read between the lines here. Yep. Yes, the acceleration is negative 9.81. Good. There is something else too if I read between the lines. Venture? Good. The initial velocity is 0. And we're looking for the final momentum, right? And just like in the example that we did, we're going to say final momentum is equal to m times the final velocity. But we don't know what that final velocity was or is. So how are we going to find it? There are multiple equations here that are valid. You're allowed to try any of those acceleration equations that you learned early on in Physics 20. A is equal to delta V over delta T. D is equal to VIT plus 1/2 AT squared. VF squared is equal to VI squared plus 2AD. D is equal to VI plus VF over 2 times T. Remember all those equations? Like you might not remember them to be able to just spout them off, but you recognize them, right? All of those are valid here. What you want to do is pick one that fits what you have, that will get you VF. So which one is it that you're going to try in this case? Yeah, VF squared. Yeah, VF squared is equal to VI squared plus 2AD. If you tried one of the other ones and it doesn't get you VF, that's okay. Just try another one, right? They're all valid. Keep trying those acceleration equations until you get the one that gets you what you're looking for. All right, we have good news here. VI is equal to 0. If it wasn't, that's okay. If the ball was thrown at 10 meters per second, then we'd simply plug in 10 for VI. Since it's 0, it makes it a little bit easier for us. We just cross it off. VF is equal to the square root of 2 times neg 9.81 times neg 30, which when we do that, we get a VF. VF, what does that stand for, by the way? We get a VF. VF is, yes, final speed, good. Works out to be 24.26108 meters per second. We don't want final speed. We want final velocity. Well, you got to use your brains a little bit here, but not very much. Final speed is 24. Which way is it going? Downwards, so we're going to make it negative 24 when we sub it in here, right? The mass is 2.00 kilograms, and the final velocity is negative 24.26108. That's the one thing with that equation, the VF squared equation, is it will never get you the velocity. It will always get you the speed. But we know which way it's going, so we can arbitrarily assign that negative value to it. All right, we do the math here. This is the easy part. Becomes negative 48.5 kilograms meters per second. Or some of you aren't big fans of the negatives. That's okay. Okay, if you don't like the negatives, just say 48.5 down. Okay, either way is okay. My preference is put the negative in the equations. We get a negative for an answer. Good. Okay, it seems to me mathematically it works better that way, but whatever works for you. Is that okay? All right, I want to draw your attention to something that we did with question number 6. Okay, Question number 6, we found the final momentum after it accelerated. You will see in Physics 30 on your data sheet, bottom left-hand corner, something that looks like this. 10 physics principles. They list those on your data sheet. They will once, twice, 3 times, 4 times on your diploma exam ask you to solve a question, but also to identify which physics principle applies or which physics principles apply. You're going to get the principle or principles that you pick from that bottom left-hand corner of your data sheet, from this list right here. Can you tell me, by looking at this list right now, of the physics principles that are listed, you can argue that there's 50 physics principles, but of the ones that are listed, which principle or principles did you use to solve question number 6 here? Yep.
1.
Yes, good. 1, accelerated motion, right? We relied on the fact that this object accelerated in order to solve this question. Uniform motion means constant velocity. Basically, if you use this equation, V is equal to delta D over delta T, it's moving at a constant velocity, the forces are balanced, okay, you've used principle 0. If you've identified that it's accelerating, you used A is equal to delta V over delta T, you've used F is equal to M times A, or any of those acceleration equations, including VF squared is equal to VI squared plus 2AD, then you've used principle 1. Does that make sense? If it accelerates, it's principle 1. Okay, I've got those written on the board at the back there. I made a couple little notes this morning for period 1. Basically what I've written up here. Those are going to stay up there, including for quizzes and tests. The idea is by the end of the year, they're going to be so old hat to you that you don't have to look up there. You're just going to know that it's this principle or that principle or whatever. Okay, does it make sense? You want to make a note on your data sheet to remind yourself of what each thing is. That's great. We'll talk about the other physics principles as we get to them, okay, as they kind of rear up throughout the course. Right now, all we've done is the first 2. Okay, let's look at question number 7. Yep.
So the conservation of momentum.
No, it wouldn't be. Conservation of momentum would not be part of that. You haven't learned what that is yet. And when you learn what it is, you'll see that although this question involves momentum, it does not involve conservation of momentum. Okay? That'll become a little bit more clear next week when we do conservation of momentum. Okay, 7 says a 1.00 kilogram rock is thrown up into the air from ground level at a speed of 8 meters per second. Ball travels up to a maximum height, then returns to the ground. What's the momentum as it strikes the ground? There is a short way to do this question, and there is a long way to do this question, and then there's a longer way, even longer than that, to do this question. Let's do the long way first, not the longer way, but the long way, and then we'll take a look at the short way. This ball goes up into the air. What happens to it as it rises up into the air? As it goes up, it slows down and stops. And then when it stops, it turns directions and speeds up, right? If I want to analyze the whole trip of this rock, let's recognize first, to find the momentum at the end, we need the velocity at the end, right? If I want to find the velocity at the end, why don't I just do this? Why don't I do pretty much the same thing as I did up here? VF squared is equal to VI squared plus 2AD. The final speed is equal to the initial speed, which was what? 8. Doesn't matter whether it's up or down because we're talking about speed. It's 8. The acceleration is neg 9.81. It slows down at 9.81 as it goes up. It speeds up at 9.81 as it comes down. If 8 is my initial speed, and I want to find the speed it's moving when it hits the ground on the way down, what's my displacement? 0. Good. Who said that? Good. 0. Like it starts at ground level. I don't care where it went to. Its initial position is ground. Its final position is ground. What's its change in position? Its displacement. 0. Okay, what does that give you for VF? VF is equal to the square root of 8 squared plus 0. 8. And then you can say PF is equal to M times VF, just like we did in the last question. Gives me negative 8.0 kilograms meters per second. That makes sense? That's a long way of doing it. The longer way of doing it, somebody this morning was talking to me about this. It's good. Like, listen, you got 6 hours to write this exam. It doesn't matter whether you do it the short way or the long way or the longer way. If you can't finish in 6 hours, even if you do every question the longest way possible, okay, we got issues. If you can't finish this thing in 6 hours, we got issues. Don't worry about time. Like, if you think of the longest possible way to do the question, who cares? Just do it the right way, whether it's the short way or the long way, whatever. A longer way to do it is to analyze the trip up. VI would be 8, VF would be what if you're analyzing just the trip up? 0. And then find the height that it goes to. And then analyze the trip down. VI would be 0 in that case. VF would be what you're solving for. And then say P is equal to M times V. What's the short way of doing it? Although you have to have a little bit of insight to catch this. Yeah? Yeah, plug what into the momentum equation? But how do you know what VF is like? Yeah, if you start at 8 and you go up and stop and then speed up coming down and end up at the same level, it has to be going the same speed, right? Just opposite direction. So some of you may have done this. Some of you may have caught the fact that, oh, if it starts at 8, it has to end at 8 as well. When would the final speed be different than the initial speed? Give me an example. Yeah, if it ends up at a different height, right? Okay, if it starts here at the edge of the desk and goes up and comes back down and ends on the floor, VF would not be 8 in that case. Then you'd have to do something like this, right? Is that good? Okay. Okay, good. Of the physics principles listed, what physics principle did we use to solve that question? Principle 1 again, right? Principle, it was not constant velocity or uniform motion. It clearly involved acceleration, so that's what we used. Okay, one more. 8. There's a 1.5 kilogram rock is thrown up into the air from ground level, reaches a maximum height of 7 meters, comes back down to the ground. What's the momentum as it strikes the ground? Sounds a lot like the last question, but we're missing something. We're missing that initial speed, which means we can't just say the final speed is the same, right? What I would suggest you do for this question is analyze half the trip. Analyze the trip down. Analyze just the trip down like we did in question number 6. If we do that, M is 1.5, of course. Delta D, the displacement, would be negative 7. Because it falls 7 meters from peak height to where it hits the ground. What would VI be if we're analyzing just the trip down? What would VI be? Who said that? 0, yeah, good. Because it slows down, it stops, and then it comes down and speeds up again. So if we're analyzing just the trip down, we're going to say VI is equal to 0. Let's solve for PF again. M is 1.50. VF, anyone? What principle are we using here? This is accelerated motion, right? Principle 1. Okay, so it's one of those acceleration equations. A is equal to delta V over delta T. D is equal to VI T plus 1/2 AT. So one of those things, right? Which one fits? They're all valid. Which one fits? Yeah, I think that's the one. VF squared is equal to VI squared. Listen, though, Venture said VF squared is equal to VI squared plus 2ED. Even if that didn't fit, even if that didn't give me the answer, it's not going to give you the wrong answer. Like, you're not going to get the wrong answer by trying that because it's valid. If it doesn't work for you, just try another one. And if that one doesn't work for you, then try another one. As long as you don't use V equals d over t, can't use that one, right? Because that's for uniform motion. As long as you use one of the acceleration ones, then sooner or later you got to get the answer. Okay, so VF is equal to the square root of 2 times negative 9.81 times d, because VI was 0, right? VF worked out to be 11.71921 meters per second. What's my final velocity? 11.71. Right? Right? Not quite, almost though. Yeah, it's actually negative, right? Because that 11.71 that I saw for here was the final what? Speed, right? And really, I need the final velocity. It's not a big thing, but if you need direction, then you sub in the negative there. Multiply those together, we end up getting negative 17.6 kilograms meters per second. Some of you may not have written this in, put the negative in there. Some of you may have just said 11.71 or 17.6. What's the other way to express it? Down. Yeah, some of you may have chosen to use the word down instead of the sign. That's fine. Doesn't matter. As long as in your mind you know that it's downward, however it's expressed doesn't matter. Good? Good? All right. I got 2 examples that I want to do with you today, and then I'm done with you guys for the entire month. I promise you. I'm done with you for the month. Okay? If you can just bear with me for the next 2 examples. All right. Example number 3, which appears on the example handout that I gave to you yesterday. It's a good one. I really, really like this question. Partly because I made it up, partly because it's just a really good question. It says a 1,000 kilogram car travels or moves at 10 meters per second. A 1,200 kilogram truck moves at 12 meters per second. What's the momentum and the total kinetic energy? You guys remember kinetic energy? Kinetic energy is found by what equation? We haven't done that yet this year. The energy of motion, right? Moving objects have kinetic energy. It's equal to 1/2 or 1/2 mv squared, yeah? Yeah. Momentum, of course, is m times v. Besides the half and the squared, what's different about momentum and kinetic energy? They both have m and v. Momentum doesn't have a half. Momentum doesn't have a squared. What else is different about those 2 things? Yeah, momentum is a vector, and kinetic energy is a scalar. That's going to become really important in just a moment here, okay? Remember that. Momentum is a vector, kinetic energy is a scalar. Okay, we want to find the momentum kinetic energy if the car is traveling north, the truck is traveling south, the car is traveling north, and the truck is traveling west. Okay, I want to say the total momentum is equal to m1 v1 plus m2 v2. Does that make sense? You can calculate them separately if you want, or we can just put it into one equation like that if we want. It doesn't really matter. Oh, I missed this. I should have really circled those. Remember yesterday I said we circle things that can cause me to make a silly mistake, like directions? Okay, that reminds me that I need a negative here, right? Okay, M1 is 1,000 kilograms times V1I, or V1, which is 10 meters per second. 1,200 kilograms times 12 meters per second, right? Is that right? Nope. Yeah, it should be a negative. The 12 should absolutely be a negative there. Okay, we add those up. We end up getting negative 4.4 times 10 to the 3 kilograms meters per second. Okay. So the momentum of the car is positive. The momentum of the truck is negative. Because the truck has more momentum, the total momentum ends up being negative. All right? Not crazy hard, but you can see how easy it would be to forget to put that negative in there. And of course, if you do that, you get the wrong answer. Listen, if this is a multiple choice question, you got to figure if you forget to put that negative in there, the answer you get will be there as an option, right? So watch that. You're going to think you get the wrong answer, or the right answer, but you don't. Okay. Okay, good. Now let's calculate the kinetic energy total. It's 1/2 of 1,000 times 10 squared plus 1/2 of 1,200 times negative 12 squared, right? 10, positive 10 because it's north and negative 12 because it's south, right? Right? No, Rachel? Yeah, right. Speed's a scalar, kinetic energy is a scalar. I don't care what the direction is for kinetic energy, we're ignoring it. Not for momentum, ever. But for kinetic energy, always ignore it. I'm going to drop that negative there. And when I do that, I end up getting a kinetic energy of 1.4 times 10 to the 5 joules. Does that make sense? Difference between kinetic energy and momentum. Difference between a vector and a scalar. Let's move on to B. Let's do kinetic energy first this time. Why do you think I want to do it first? Because it's easy. It's easy. The total kinetic energy in B is what? Sean? Same as it is in A. How do you know that without doing any calculation, Sean? Because energy is a scalar, and it doesn't matter whether it's going north and south, north and north, or north and west. The kinetic energy won't change, right? Think about it this way. Like, if something hits you, it's because of the kinetic energy that it hurts. It doesn't matter whether it hits you from the north or it hits you from the west, it hurts the same, right? The direction doesn't matter. Okay, but it does matter for momentum. How are we going to tackle the whole north and west thing here? How are we going to tackle that? We have to add vectors, just like we did in A. We have to add vectors. But we're going to do it a little differently. How are you going to add these vectors? Yep. Yes. Let's draw a picture. Let's say that we have a momentum to the north. We've got a mass of 1,000 kilograms. We've got a velocity of 10 meters per second. That gives us a momentum of what, 10,000 kilograms meters per second. We also have a momentum to the west. The mass was 1,200 kilograms. The velocity was 12 meters per second. And the momentum was 1.44 times 10 to the, what would that be? 4? Right, m times v. This would be the resultant velocity, the sum of those vectors. We added these vectors up here by just adding a positive to a negative. We add these vectors down here by doing, as somebody said a minute ago, the Pythagorean theorem. So 1.44 times 10 to the 4 plus 10,000 squared. Solve that. It works out to be 1.8 times 10 to the 4. Right? Does that make sense? You know, things are getting a little harder now, right? Not insane, but certainly harder than it was yesterday. Final answer? Oh, what's wrong, Patrick? Yes, momentum is a vector. We included direction up here, said it was negative, or said it was south. We need a direction here. That's going to be in the form of an angle. Theta is going to be equal to the inverse tan function of opposite over adjacent of 1.44 times 10 to the 4, opposite over adjacent. The angle that I get there is 55 degrees. Okay, I'm going north and west. Is it north of west or is it west of north? What is it? It's west of north. Good. West of north. Look. I went north. And I measured my angle from the north. This is north. I measured it from the north. So I'm going to say it's west from the north, or west of north. So kinetic energy, you can see that no matter what the direction, kinetic energy is going to be the same. But momentum will be different depending upon the direction, because kinetic energy is a scalar and momentum is a vector. Somebody said it. One more example, and that's it. You're going to have one question to work on after this, but I'll be done. The momentum of an object is 200 kilograms meters per second. What does the momentum become if the mass is changed to twice what it was and the velocity is reduced to 1/3 of what it was? How do you solve for a momentum when you don't know what the mass and the velocity are? You know what it's changed by, but you don't know what it was to begin with. Well, let's say you did know what the mass was and you did know what the velocity was. So you knew m and v. What would you do? What equation would you use if you know what m was and you know what v was? I'll give you a hint. This is the easiest question ever. If you know what m is and you know what v is, how do you find momentum? M times v, right? Let's write down that equation. Find a relevant equation to the problem. That's my relevant equation. Now I'm going to put a little subscript here, an O. That's going to mean original or old. This is the original momentum before I make changes. The original momentum, the old momentum before I make changes is m times v. Guess what? It's also equal to 200. Nothing groundbreaking here, right? My data sheet tells me the momentum is m times v. The problem tells me the original is 200. So I haven't really done anything here. I just picked an equation from my data sheet, and I picked a number from the problem. This is what my momentum is before I make any changes to it. Now let's make some changes. We're going to call this Pn now. What do you think the N stands for? New. This is my new momentum. This is my old momentum, my new momentum. I'm going to let you in on a little secret before I go any further. Yesterday I told you the equation for momentum is m times v, right? Well, I kind of lied. The equation for momentum is mass times velocity. We represented that by m times v. Does that make sense? What if velocity had a symbol u? The equation would still be mass times velocity, right? How would we represent it then? M times u, right? That makes sense? So the equation is, I mean, really it's m times v, right? Really, for all intents and purposes, because we always call the velocity v. But it doesn't have to. I'm not going to call it m times v here. My equation for my new momentum is still mass times velocity, but my new symbol for mass isn't going to be m. Anybody want to take a stab at what it's going to be? Yeah? It's going to be 2m. That's my symbol for mass now, because it's twice what it was. If it was m, now it's 2m. What's my symbol for velocity now? Not v anymore. My symbol for velocity now is, yeah, Caitlin? Yeah, 1/3 v. Now, let's simplify this a little bit. 2 times 1/3 is 2/3. See what I did there? Same thing, I just simplified it a little bit. Good news, though. What's mv equal to? Look, mv is equal to 200. That's what we wrote down in my first step. So I'm going to say the new momentum is 2/3 times 200. And when I do that, I think I get 133. Is that right? So what are the steps involved in solving this problem? Write down an equation from your data sheet. That's easy. It's the second thing. Write down the number that's given to you in the question. The original momentum is mv, and it's also equal to 200. And then change your equation around. Instead of being m, it's 2m. Instead of being v, it's a third v. And then simplify it like we did right here. Let's replace the mv with 200. Done. That makes sense? Okay, I don't have a full worksheet for you on this. All I've got is one question that I'm going to ask you to sit and do at your desks here right now. If you have trouble with it, we'll go over it. Otherwise, that'll be it. Everybody got that copy down? Yeah? Okay, just take a look at this question here. You don't have to copy that down if you don't want, but just somewhere in your notes, just try doing that question. I'm gonna help you out just a tiny bit at the start, and then I'll set you free on it here. It says the velocity is 20. We're looking for what the velocity would be if the momentum is half and the mass is. What's my equation here? What's my relevant equation? Sorry? P is equal to m times v. Yeah, kind of. But what are we trying to find the effect on? Velocity, right? So what am I going to do? Just rearrange it. My original velocity is p over m. My original velocity is 20. And then go from there, right? My new velocity is whatever. Change the value of p, change the value of m, and so on. So sometimes you got to take an equation from your data sheet and then rearrange it. Sometimes you just take the equation from your data sheet directly. Okay, let's see what you can do with this next couple minutes at your desks, and then we'll call it a day.